In this lesson, we're going to talk about the speed of sound in air, resonance, and standing waves. We're going to calculate the speed of sound in air and resonance lengths of open and closed air columns. As we've discussed in previous lessons, sound waves are longitudinal pressure waves that propagate through a medium. The speed of sound depends on the medium in which it propagates through. Some physical properties of the medium that determine how fast sound travels are things like density, temperature, the state, so if it's solid, liquid, or gas that it's traveling through, will all affect the velocity or speed. The following equation is the approximate speed of sound in dry air, so we're talking 0% humidity, at temperatures near 0 degrees Celsius. Here, your speed of sound in air is going to be in meters per second, of course, and your temperature is going to be in degrees Celsius. This equation gives good predictions in relatively dry, cold, low pressure conditions, such as the Earth's stratosphere. Now for an example, what is the wavelength of a 225 Hz wave produced in air at negative 20 degrees Celsius? Let's write down our givens. So we know our frequency, we know our temperature, and we want to find out our lambda, which is our wavelength. Well, I'm tempted to use the equation we just talked about to find out our speed. So your speed in sound is going to be 331.6 plus 0.606 times your temperature, which in this case is negative 20 degrees Celsius. And that gives you 314.48 meters per second. Now that we have our speed, we can use this equation. Your velocity is equal to frequency times lambda, which is your wavelength, and let's solve for wavelength. So that's just rearrange this equation, velocity over frequency, and that's going to be what we just solved over your frequency, which was given in the question, 225 Hertz. And that will give you 1.42 meters. And remember that Hertz is 1 over second, so your seconds are going to cancel out and you're left with meters. So therefore, your wavelength is 1.42 meters. Next thing we're going to talk about is resonance, which is defined as the increase in amplitude of a wave due to the transfer of energy in phase with the natural frequency of the wave. Frequencies at which standing waves form are known as resonant frequencies, and we're going to be looking at more of those later on in this lesson. Resonance can be most clearly seen in musical instruments, namely in open-end and close-end instruments. The most famous example of resonance is an opera singer singing so loudly that she shatters a wine glass with her voice. So every physical object has a natural resonant frequency, and that's the speed at which it will vibrate if bumped or otherwise disturbed by some kind of stimulus, such as a sound wave. So if an opera singer can actually match that natural resonant frequency, then the glass will shatter because it'll be too much for the glass to take. Many musical instruments will use some kind of air column as part of its component. If both ends of the tube or column are uncovered or open, the musical instrument is said to contain an open-end air column. Some examples of this include the flute, recorder, even some organ pipes. And as we can see here, this pattern of waves is called a standing wave. As you can see in this kind of situation, we have antinodes right here. I'm just going to call it A. here, so antinode, antinode, antinodes here as well. And our node is going to be right in the center, so this is your node. This is known as the fundamental frequency in an open-air column, and it's also known as the first harmonic. Now let's call the length of the column or wave L, and we can see that L, the length, is half a wavelength. In the next situation that we're going to be looking at, we have a slightly longer tube, and so our nodes are going to be here and here. Our antinodes, of course, are going to be at the ends because it's an open-air column. We also have some antinodes right here and here. So in this situation, we have 3 antinodes and 2 nodes, and this is known as a second harmonic. Your length is equal to 1 wavelength. Since, as you can see, this wave starts from a crest and then ends at a crest. And this starts from a trough and ends at a trough. Similarly, the third harmonic will follow the same pattern. Here we have 4 antinodes and 3 nodes, and the tube length is going to be 1.5 lambda, or wavelengths. So here's a summary table showing us what we've just found. And we have our number of nodes, antinodes, for each harmonic, and your wavelength, or the length of the tube. I hope you all noticed that there's a pattern, and that pattern is that length is equal to n, which is going to represent our harmonic number, times your wavelength divided by 2. And if you notice, if you go back, you'll notice that this is consistent with our findings. Okay, now let's talk about closed air columns. When a wave enters a closed air column, an antinode is once again established at the open end of the column, just as before, and the closed end of the column has air that is still, thus creating a node. So this is what it looks like, and if you notice that only a quarter of a wavelength, so from the, if we're going this direction, from the crest to the midpoint, that's a quarter of a wavelength, and that's what can fit into the tube under these conditions. Keeping with the above concept of antinodes at the open end and a node at the closed end, the next possible pattern that can be done is the third harmonic. And here we have 2 antinodes and 2 nodes, so only 3/4 of a wavelength can fit into the tube. Keep in mind the closed air column acts like a sine wave since it starts at the equilibrium, and we need, for full cycle, this would be 1 period right there. So we have 3/4 here, so it's really useful to be familiar with the sine wave. So looking at the fifth harmonic, we have 3 antinodes and 3 nodes as seen below, meaning that 5/4 wavelengths will be able to fit into the air column. And notice for the closed air column scenario, it skips a harmonic, so you're just looking at the odd numbers, 1, 3, 5, 7, 9, and this is just because of the asymmetry of the closed air column. So here is a summary for the closed air column harmonics. And if you notice here, we just solved for lambda instead of L. So when we've been doing it, we've been solving for L, so this is just rearranged. Here are your number of nodes, antinodes, number of waves per column, and rearranged. So in general, our pattern here is going to be your length of the column is equal to n, which is your harmonic number, times lambda over 4. A tuning fork with frequency of 256 Hz is held above the closed air column, while the column is gradually increased in length. At what lengths for this air column would the first 4 resonant points be found if the speed of sound in air is 333 meters per second? Okay, so we're working with a frequency of 256 hertz, and we know the velocity or speed of sound in air, is 330 meters per second. So why don't we figure out what our wavelength is, and we can use our V is equal to F lambda equation, and rearrange for lambda, which is V over F, and lambda is going to be 330 meters per second over 256 hertz, which is 1.29 meters. So we have our wavelength, and now we know this is a closed air column, so we're going to be using the second scenario that we did. So first harmonic for that would be lambda over 4, which is just 1.29 meters over 4. And that gives us 0.32 meters. Remember, because this is a closed air column, it's going to skip one. So we're finding our third harmonic next, and that's going to be 3 lambda over 4, which gives us just 3 times 1.29 meters over 4, which is 0.97 meters. And then our fifth harmonic, or resonant point, is going to be 5 lambda over 4, which is 5 times our wavelength over 4. That gives us 1.61 meters. And now we need 4 points, so our 7th harmonic is going to be 7 lambda over 4, which is just 7 times 1.29 meters over 4, and that gives us 2.26 meters. So those are our first 4 resonant points. Wave interference is the phenomenon that occurs when 2 waves meet while traveling along the same medium. Beat frequency is defined as the frequency of a periodic pattern of constructive and destructive interference that occurs when waves of slightly different frequencies interfere. If 2 waves of equal amplitude and slightly different frequency, F1 and F2, combine, they will produce a beat that has a frequency given by this expression. So your beat frequency is equal to the absolute value of F1 minus F2. So it's just basically the difference between the 2 frequencies. An example of this is 2 singers sing slightly off key. One sings a note of 260 hertz while the other sings at 262.1 hertz. What is their beat frequency? So let's write down our givens. So to calculate our beat frequency, we're going to use the equation F1, the absolute value of F1 minus F2. And that will give us negative 2.1, so just positive 2.1 hertz. And so therefore their beat frequency is 2.1 hertz. As another example, a sound of frequency 550 hertz is combined with another to produce a beat frequency of 5 hertz. What are 2 beat frequencies for the second sound? Let's write down our givens. Okay, so because we're using our equation for beat frequency, it can be positive or negative. So if we were going to, so you have 2 options here. First case is that your second frequency is equal to the addition. So we're just moving around that first equation, or the original equation, and that's going to be 550 hertz plus 5 hertz, which is equal to 555 hertz. Your second option would be if you subtracted your beat frequency, so this is in the case where it's negative, and that's equal to 550 hertz minus, so the discrepancy is on the other side, and we get 545 hertz. And so your two beat frequencies are either 555 hertz or 545 hertz. And that's it.